Welcome to SICSS-Covenant tutorial series. I am Emmanuel Olamijuwon, and it's my pleasure to introduce our tutorial lead for this session, Dr. Andrea Gilardi. Dr. Gilardi is a research fellow in statistics at the University of Milano Bicocca, Department of Economics, Management, and Statistics. He works mainly on spatial and spatial-temporal models for data on street networks, such as car crashes and ambulance interventions. He is the author of two R packages that ease the management of spatial data in R. Of interest today in particular, Dr. Gilardi will introduce the SF network for tidy geospatial networks in R. Thank you very much for joining us today, Dr. Gilardi. Our virtual stage is yours.
And as you said, I'm a research fellow in statistics at the University of Milano Bicocca, and I'm here to present a talk which is entitled SF Networks, Tidy Geospatial Networks in R. This SF network is an R package, and it is a joint work with Lucas van der Meer, Lorena Abad, and me and Robin Lovelace. So, as you said, I'm the author of this package, and I'm the author of also another package that focuses on the analysis of data obtained from OpenStreetMap, and that this other package is named OSM Extract. The idea of both packages is to download and to analyze the road network that are downloading from OpenStreetMap. The point is that in the last years, more or less when I started my PhD, there was a surge of interest in the analysis of data that occur in road network. For example, in the last years, I work on the analysis of car crashes and ambulance intervention. If you imagine, these are two types of data that are constrained to lie on a network domain, since, clearly the cars are constrained to lie on the street network. The point is that if these type of events, they are constrained to lie on this type of network, then also the spatial analysis must take this fact into account. And so we are developing a set of tools that can be used to perform these operations. This is my web page if you want to check more details. But anyway, I think we can start with the presentation now. So I will share you now the link for the slides if you want to follow the slides. Where's the chat here? So this is the link for the slides. Please let me know if the link doesn't work. Also, these slides are created using R Markdown, and also in the, let's say, in the second part of this presentation, I will focus on, let's say, hopefully an interactive R session. And for this R session, I prepared the script, and this script, the slides and the markdown and all the figures, they are saved in this GitHub repository that I will share with you now. Here. Did you receive the links?
Yes. Yes.
Perfect. Okay, so this was the idea of my schedule for this presentation. At the beginning, we are talking about the geospatial networks and the motivations and the reason why we decided to develop this R package. Then we will focus, we will just try to visualize the main preprocessing functions. This preprocessing function is just a little bit in all, let's say, all the universe that is behind SF networks, but I think it's the most important step when you try to analyze geospatial data. The point, is that, as you know, maybe if you're working with also machine learning models, there is a motto that says garbage in, garbage out. Here is the same. So if the input data has several problems, then the sooner you detect these type of problems, let's say the easier is the type of analysis. So first, I will try to focus on present the package, focus on the preprocessing functions, and then we will move to a live demo where we will try to code some of these examples. At the beginning, there is some time for questions, or if you want, we can just code more examples. Just to let you know, this tutorial is based on the GitHub version of the package. So there are some super tiny differences between the GitHub version and the Cron version. If you want, if you haven't already installed the GitHub version of sfnetworks, then you can run this line of code in R. I will copy here. This line of code requires also the R package remotes. So if you haven't already, you have to install the R package remote, and then you have to install this line of code. The only thing to notice here is that the SF network packages has dependence, as we will see, on SF and tidygraph. These are two other R packages that might be difficult to install. So if you have any problem running this line of code, so if you have any problem installing the package, please let me know as soon as we move to the R coding session. Okay. So the idea is that this package is called SF Networks and focuses on the analysis of geospatial networks in R using a tidy workflow. The idea, again, is that we want to analyze geospatial networks. So we want to analyze, for example, here we have an example of a geospatial network, which is a set of rivers. Geographical networks are thought of as graphs embedded in a geographical space. For example, again, here we have a graph that represents a set of rivers. Other examples are, for example, street network. The main characteristics of this type of networks is that the nodes of the network are usually associated with points in the space. The edges of the network are usually associated with lines in the space. If you know the simple feature terminology, the simple feature standards, we say that the nodes are associated with the so-called point geometry. The edges are associated with the so-called line-string geometry. The key fact here is that when you analyze geospatial networks, you cannot separate these two dimensions. So you cannot separate the graph dimension and the spatial dimension. If you want to analyze this type of data, you have to take both dimensions into account at the same time. And so the objective of our package, in fact, is to ease this project and this process and to improve let's say, the merging of this graph and spatial operation for all the people that want to analyze geospatial data. As we said, here we are not only dealing with the analysis of geospatial networks, but we are dealing with the analysis of geospatial networks using a tidy workflow. This means that most of the function in let's say, the application in the SF networks package are integrated with several packages that belongs to the so-called tidyverse. The tidyverse, I mean, as you probably know, is one of the most important collection of packages for data science, probably the most popular one. All packages in this, let's say, universe, they share the same design philosophy, and they are based on the concept of tidy data structure. In this case, our idea is to try to convert some of the ideas that are common in the, let's say, in the tidyverse workflow for the analysis of geospatial data. For example, in this case, I just want to show that here on the left we have some line of codes. For this line of codes, we are first in the first two line of codes load the package tidyverse and SF networks. In the next line of codes, we will just want to show that one of the keys example in the SF network package, which is the object voxel, is nothing more than a table. A table is like a tidy re-implementation of the so-called data frame. The idea is that we have like a classical data frame structure where that has, let's say, some tiny difference with respect to the classical data frame. And this SF network implementation builds on top of the table class. Then, as we said, here we are focusing on geospatial networks. And so we have the two key ingredients that were used for the development of this package are the SF package and the tidygraph package. The SF package, as you have probably already studied, is probably the most, at the moment, is probably the most important R package for the analysis of the vector data in R. This is a very popular package because it implements a so-called standardized storage for geographical feature. For example, the idea is that the authors, they wanted to provide a set of so-called standard features or simple features that can be used to represent each type of data. There are many type of features, but here we will just focus on the simplest one. In this presentation, we will just focus on the so-called point, line, and polygon features. The idea is that just using this type of features, we can represent several sets of objects. And in fact, for the moment, in the SF network package, we support only objects that are created using points and line geometries. Point geometries are clearly just a set of coordinates. Line string geometries are ordered list of coordinates. For example, here I'm showing you 3 line strings. Each line string, as you see, the first line string is composed by 2 points. This one is the first point. This one is the second point. The second line string is composing by 3 ordered points. The most important fact is that here this SF object has additional characteristics. For example, here we can see that this object has a so-called CRS. CRS stands for Coordinate Reference Systems, and this string details the coordinate reference system that is used for represent this type of data. This WGS84 means that probably these are longitude and latitude data that are specified using the ellipse WGS84. Then again, we are dealing only with line string geometries that are specified using only the X and Y dimensions. So we are dealing with 2-dimensional data. On the other side, as I said, we are not only dealing with spatial objects, we are dealing with graph objects. Since geospatial networks, they are at the same time spatial object and graph objects. So our idea was to merge the SF package and the tidygraph package to create a unique structure that can be used for the analysis of geospatial data. This tidygraph package was developed by Thomas Pedersen, and this tidygraph package provides a very powerful tidy implementation for the iGraph package. The iGraph package is probably the most important R package for graph analysis, and this tidygraph package provides a tidy implementations for graph analysis. The idea was that when the author decided to start working on graph analysis, they decided to implement this type of structure. So they decided that if you want that, I mean, the problem is that when you want to work on this type of data, so when you want to work on graph data, it's really difficult to define a tidy data frame that represents graph data. Since graph data, they clearly have a relational structure. So if you want to represent graph data, then you have a set of nodes and set of edges, and then you have some sort of relationship between nodes and edges. So it's really difficult to have just one set of data, with just one set of tidy data to represent a graph structure. For this reason, the authors decided to implement a tidy graph object that models a graph as a collection of 2 tables, so 2 data frames. So they have a data frame for the nodes, a data frame for the edges, and then they have a set of indices that connects the nodes and the indices. For example, here on the left, we have a super simple structure. So we have a graph with 3 nodes and 3 edges. The nodes are described here. So we have just 3 nodes, and these nodes have a name that is A, B, or C. The edges, on the other end, they have no particular characteristic, but the edges are described just from 2 columns of indices, which are named from and to. These 2 columns describe the index of the corresponding nodes that, let's say, are associated to a given edge. So our idea was to combine the SF package, the tidygraph package, and define the so-called sfnetworks package. The sfnetworks package is the combination of the SF and the tidygraph package for the tidy analysis of geospatial networks in R. As I said, the idea of the tidygraph package is to define a node and edge data for the analysis of geospatial data. In fact, the authors on the web page says relational data cannot in any meaningful way be encoded as a single tidy data frame. So the problem is that if you are dealing with geospatial data or with relational data, you cannot create a unique table to describe nodes and edges data. So they say that a close approximation of tidiness for relational data is two tidy data frame, one described in the node data and one described in the edge data. Our idea was that actually we could, let's say, just slightly adjust this sentence, and we say that a tidy approximation for geospatial data is the combination of two simple feature objects that describe the nodes and the edges. So we have one simple feature table that describes the points. For example, the points, imagine that is, for example, the crossing between the streets or the intersection of two rivers or any other points that can describe a segment, a street segment. The edges, on the other hand, they are actually the segments that describe the roads or the rivers. So the idea was that, for example, here I have a simple feature table of line string. The idea is that we have one simple feature table of lines, one simple feature table of points. And if we combine these two tables, we have a unique sfnetwork object that describes the spatial dimension, that describes the nodes and the edges. So this is, for example, the printing, or the first example of an sfnetwork object. An sfnetwork object has, I think, a really beautiful printing method. For this printing method, we have a description of the sfnetwork object. We will see many examples later on in the, let's say, in the interactive tutorial. Here, I just want to say that for this example, we have that the first line gives a brief description of the nodes and the edges. Here we have that this sfnetwork object has approximately 700 nodes and 850 edges. The next line describes the coordinate reference system of the nodes and the edges. Again, as I said, here we are dealing with spatial data. So it's crucial when you want to represent and you want to store geospatial data. It's crucial also to store the coordinate reference system of these objects. Moreover, for the sfnetworks package, at least, you have to use the same coordinate reference system for the nodes and for the edges. So here, since the two objects have the same dimension, we just show the coordinate reference system for one of them. The next line, which is the third line, gives a brief description of the graph structure. So here we have a directed multigraph with 14 components with spatially explicit edges. So spatially explicit edges means that in this case we are dealing with an sfnetwork object where the spatial dimension is formed by a set of geometries instead of just a set of edges. This means that when you want to create let's say this geospatial structure, you always have a spatial dimension for the node. You may or may not have a spatial dimension for the edges. If you do not have an explicit spatial dimension for the edges, then sfnetworks implicitly assumes that you have a direct segment between each pair of nodes. So it assumes that there is like a straight line segments that connect the pair of nodes. We will see later on what this means. But then I just want to say that the first three lines briefly describe, let's say, the generic structure of the sfnetwork objects. The next lines describes the node SF table and the edges SF table. In particular, here we have that the node SF table is a table with 701 points, and then we have a brief description of the variables. The same works for the edges data. So, as I said, now I just want to briefly briefly present the network preprocessing function and cleaning function. Here, in my opinion, I mean, I want to stress a lot that here we have several possibilities when you work with this package. But the most important one, in my opinion, is that if you want to work with this type of data, you have to be sure that you are working with a clean geospatial object. So you have to be sure that you are not, let's say, there is no, let's say, problem, technicalities, or whatever you want to call it, that may ruin your spatial analysis. For example, here we have like this type of data, and I want to show you some pre-processing operation that can be used to clean or to tidy this set of data. For example, here in this case, we will see that the yellow segment here and the light blue segment here, actually they are so-called redundant edges as soon when you're dealing with routing operations. The point is that the yellow segment connect a vertex with himself. So I mean, clearly maybe there is some existing road and there is some building here that connects whatever. The problem is that when you want to, say, run a routing algorithm on your network, then this edge it doesn't do anything, since it just connects the same vertex to itself. The same also here, if you consider these segments and the yellow segments, they both connect the same two sets of vertices. So here the problem is that you have, let's say, two edges that start from the same point and arrive at the same point. Clearly they are redundant here, at least if you want to think on a routing perspective. So we define a set of tools that can be used to simplify all of these operations. If you run this set of tools, and later I will show you how, we arrive to this type of edges. So here you see that we removed the light blue segment and we removed the yellow segment, since if you want to work on a routing mindset, these segments are redundant. Then again, here you see that we have some intersection between the two segments. Let's say some spatial intersections. The problem is that sfnetworks does not recognize this geospatial intersection. sfnetworks recognize geospatial intersections only if there is a vertex at the intersection. So if you want to recognize also this type of analysis, then we implemented another operation that can be used to add a vertex every time there is an intersection between two segments that is actually an intersection. The problem is that this operation, as we will see, is quite tricky, since the problem is that here, I mean, usually I focus on the analysis of street networks. So the problem is that we absolutely do not want to create artificial intersection. For example, imagine that there is a bridge and there is a street behind the bridge. There is an overpass and there is a street that goes below the bridge. If you imagine that you are projecting this type of data in a 2-dimension, then the overpass and the underpass, they are intersecting. The problem is that they are not really intersecting. So for this reason, we implemented a set of checks, let's say, that they actually create an intersection only when there is actually an intersection. So in this case, we assume that there is actually an intersection and we add this black dot. If we add this black dot, then sfnetworks understands that there is really a connection between these segments and this segment. I mean, just to be sure, you can see my mouse, right?
Yes, yes.
Okay, perfect. And the next one, I mean, just two things more, and then we can move to, let's say, to the R coding session. Here we also implemented a set of tools that can be used to smooth, to remove the redundant edges and the redundant vertices. So the point is that here, for example, just imagine this vertex and this vertex. Again, they are redundant from a routing perspective, since the point is that if you want to go from here to here and you arrive to these intermediate edges, then the only thing that you can do is keep going to the right. So this vertex is actually redundant. The same also for this point. So if you're going from south to north, then you go north, and then when you reach this vertex, you can only keep going north. So this is actually quite redundant from a routing perspective. Lastly, we implemented a set of tools that can be used to simplify roundabouts. For example, just imagine that these 4 segments, they represent a roundabout. Actually, we may want to be interested in a simplification of this type of networks. The problem is that, for example, when you run this type of algorithms for a large city, then you're dealing with hundreds and thousands of segments. I mean, just imagine that, for example, there is a segment every 200 meters. So it's really easy to understand that these type of segments, these type of networks can be really large. So we implemented a set of tools that can also be used to simplify these type of intersections. So just imagine here we have these 4 nodes that are really close to each other. The idea is that we merge these 4 nodes, creating just a unique node here that preserve the same structure as the other nodes. So we implemented a set of tools that can be used to go from here to here. Let's say the structure at the end is the same, but the problem is that this network is much more simple and has much less routing problems than the other type of network. So if you have any question now, please ask. Otherwise, we can move to the live coding, to the R script. So for the R script, I will share with you the code now. Here, no, oops. Here. You can just copy the code and paste the code in RStudio or whatever editor you use for running our code. Here I will use RStudio. Perfect. As I said, the tutorial is based on the GitHub version of the package. Notes. Okay, as I said, it might be difficult to install this R package since some of the dependencies might be difficult to install. For example, the SF and the tidygraph package might be difficult to install. If you have any problem installing this package, please let me know and we can sort it out. Otherwise, if you don't have any particular problem, I think we can start with the tutorial. So first, just load the packages.
Yeah.
Let's close here. So first, it's just an option. This option is used to control the number of features that are printed by sfnetwork. It's not something super important. I think it's just, in my opinion, it's nice to display a little bit more than the usual structure. So, as I said during the introduction, an sfnetwork object is just the union of 2 SF objects. So again, the idea is that when you want to analyze relational data using tidygraph, then tidygraph represents the relational data using 2 sets of tables. One set of tables is for the edges, one set of tables is for the nodes. Here we have more or less the same idea. So we have one SF objects for the nodes, one SF objects for the edges. So just to give you a brief example, I want to create an SF objects for the nodes. Here, the SF object is just a list of 4 points that are scattered somewhere around the globe, and a set of edges. These nodes and these edges, they have just a set of coordinates. For example, here we have 4 points, 1, 2, 3, 4. These points have a coordinate reference system. Then we have an edges table. This edges table again has 3 lines, here 1, 2, and 3. The first line, for example, connects the first point and the second point. The second line connects the first point and the third point. We can also see the same idea when we check the index of the table. So, for example, here we can see that the first edge connects the first point and the second point. The second edge connects the first point and the third point, and so on. As I said, the two objects have a coordinate reference system, and the two objects must be created using the same coordinate reference system. So let me create the set for the nodes, the set for the edges. Then, if we want to finally create this sfnetwork object, we can use the sfnetwork function. First, we have to use the nodes, then we have to pass the edges. When we run this function, we can see that there is an output. The output says that the spatial network structure is valid. This means that actually this index actually corresponds to the given point. So for example, here, if we insert the coordinates of any other point, but the index says that this first line connects the first and the second point, and actually this point is not the second point, then the function throws an error. So the function checks that there is a correspondence between these indices and these coordinates. Now we can print the object. The printing of the object is similar to the printing of the object that I showed you before. The first line summarizes the structure of the sfnetwork object. So we have 4 nodes and 3 edges. So we have 4 points and 3 lines. Then we have the coordinate reference system. Then we have a description of the graph. We have a directed cyclic simple graph. This means that we are dealing with a directed graph with no cycle, and a simple graph, meaning that there is no self-intersection. We have 2 components. Components are the groups or fully connected nodes. And then says that we have spatially explicit edges. Then again, we have a description of the node table, and we have a description of the edges table. Here we also notice that here it says that the node data is the active table. This is really important since, as we will see, in the tidygraph representation, they do not only create, let's say, 2 sets of tables. So they have a set of table for the nodes, a set of table for the edges, but they also have a way to design which of the 2 tables is active. Active means that when you run a spatial operation, for example, you want to calculate a betweenness coefficient, you want to compute a centrality measure, then this centrality measure are applied to this table, which is active. So we do not have to define a separate function for the edges for the node table. We have to define just one function that can be used to switch between nodes and between nodes table and edges table. Then this function, I mean, we will see several examples. This function, they are usually applied to the active table. So, I mean, that's what I said. So now we can finally create the first plot here. So this is our first plot. This first plot is like the default plot for the sfnetworks objects. We have that there is a point for each vertex and there is a line for each edge. As I said, in this case, we are dealing with the geocoded objects. So clearly, these points, they are not only represented, let's say, in a geospatial setting, as a graph objects, but these objects, they are represented, they are scaled using an appropriate coordinate reference system. So this is just a super basic representation. I'm not going to say showing something super fancy, but we also implement a slightly more, let's say, a slightly more fancy way to represent sfnetwork objects, which is based on autoplot. The idea of autoplot is to create a super simple ggplot objects that can be used to represent this type of networks. The idea is more or less the same. So we have these ggplot objects that can be used to represent this type of sfnetwork object. Again, we have 4 points and 3 lines. Each point is a vertex and each line is an edge. So Then we are dealing, I mean, as I said, the SF network object is just a union of two tables, but to create this union of two tables and this connection between two tables, we have to use the SF network function. On the other hand, we can also move it in the other direction. So given an SF network objects, we may want to extract the table for the nodes. The table for the nodes can be extracted running st as sf, and then we specify the object, the SF network object, and then the name of the table. So when we run this line of code, we can see that we are dealing with an SF network object and we are extracting the nodes table. The same also for the edges table. I mean, we can skip here. And here I just want to stress that when you try to create, here I'm at line 93, when we want to create an SF network object starting from the nodes and the edges table, by default we are creating a directed network. Directed network means that we can travel in one edge only in one direction. The problem is that usually this may be too restrictive. For example, if you have, let's say, some toy data that they represent, for example, a maze or whatever you want to think, maybe you want to create a non-directed network. If you want to create a non-directed network, you have to set the argument that the directed equal false in the call to SF network. Here. Here you see that we can recognize that this is an undirected network, since the description says that we are dealing with an undirected simple graph.
They give more than 40 online courses really free if it let you work, like the source meetings with
So for the moment, I just created an example where we create an SF network object starting from a table of edges and a table of nodes. The problem is that usually when we run this type of analysis, we want to create an SF network object that starts only from a table of edges. So the idea is that given a set of segments that represent a set of street segments, we want to create a road network starting from the set of segments. So in some way, we want to start from just the segments that represent the streets, and we want to infer, let's say, a graph dimension using just this set of spatial segments. For this reason, we implemented an algorithm that can be used to perform this operation. For example, here I will just show you this for segment. For example, imagine that we have this 1, 2, 3, 4, 1, 2, 3, this set of segments that are showing the streets. The idea is that, but let me just do something. Okay, I think it's more clear now. Maybe a little bit more. Okay, so we have these 4 segments. Each segment has a different color, and we want to go from this set of segments to a graph representation. To perform this operation, we can use this SF network function. The first argument that we have to pass to SF network is a set of edges. This set of edges, then in some way, we pass from this set of edges, this set of spatial edges, to a graph network. Again, here we specify directed equal to false, since we want to stress that we are dealing with a non-directed edge, with a non-directed network. If we print this type of object, we can see that there is, I think, a beautiful summary of this type of edge. So here it says that we are dealing with an SF network object with 4 nodes and 4 edges. The 4 edges are clearly the four segments that were passed as input. So the orange, the green, the blue, and the pink. And the 4 nodes are defined at the common boundary points of these 2 edges. For example, here it says that the common boundary points are at 0, 0 here, at 2, 0 here, at 0, 1 here, and at 2, 1 here. 0, 1 was here. So we do not have an intersection between the orange and the green line, and again between the orange and the green line. For example, you can imagine that the orange line is an overpass, the green line is an underpass. So even if we have, let's say, a so-called spatial 2D intersection between the two sets of segments, we do not really have an intersection between them, since actually the two sets of segments do not share a point. So here we have an intersection only when the segments share points in their boundaries. So here is explained a little bit more precise. So the provided lines, so the straight segments, represent the edges of the networks. The nodes are created at their endpoints. Endpoints that are shared between multiple lines become one single node. So the idea is that given a set of segments, these segments represent the edge dimension of the graph. The boundary points of these edges represent the graph dimension of the graph, the vertex dimension of the graph, and then the connectivity between the graph and between the nodes and the edges is determined by checking which boundary points are shared between the edges. If two edges share a boundary point, then we say that these two edges are connected. So I think this is just the basic idea for the algorithms that we use to pass from a set of segments to an sfnetwork objects. So now we can go to we can start reading some, let's say, real world data. I think that you can get this type of data from the GitHub repository. If you have any problem reading this type of data, please let me know. This type of data, they are shared in this GitHub repository. They are here. I'm sorry, I don't know how to pronounce that, but it should be ajj.jpkg, and it should be I think it's a region in Nigeria. And the idea is that given a set of segments that is located somewhere in the world, we can convert this set of segments to an sfnetwork objects. So we can run this line of code. Unfortunately, this line of code returns an error, since, as I said, at the moment we can only work when the input data is as a point geometry or a line string geometry. So the idea is that first we want to convert the input data to a line string geometry, so this line, and then we can run the usual function. Finally, print the object. We can print the object now. The object here is a much more complex object than the other one. So we can see that we have an sfnetwork objects with approximately 14,000 nodes and 900 edges. So it's a much larger object than the other one. The coordinate reference system is the usual one, so WGS84. So we are dealing with latitude and longitude data using this type of ellipsoid. Then here it says that we are dealing with an undirected multi-graph, so we are dealing with a non-directed graph with 509 components. 509 components, meaning that there are several groups of segments that are connected to each other, but that do not share any point with the other groups of points. So then we can see that we have these nodes, this set of node data. The node data is just a list of points, and then we have the edge data. Here, in this case, we have something that is even more, let's say, rich than the other type of data. So we have not only the coordinates of the lines, but we also have a description of the type of the segment. So here we have a description saying that, for example, the first edge of this network belongs to a road which is a residential type. This type of segments, they were obtained from OpenStreetMap. So let me share you something. If you go to the OpenStreetMap website and you check the highway page here, just one moment. So here, in this page, we have a precise description of what it means that this segment is a residential type. So we just have to go down. A residential road is a road which serves as an access to housing. So I will share you the link. So here we have that we are not only dealing with a set of points and a set of edges, or a set of points and a set of segments, but in this case, the segments, they also have a field that enriches the description of the set of segments. So finally, we can start plotting this geometry. I mean, here you will see that it will take a little bit more. Just let me zoom a little bit less. Here we can see this beautiful structure. So we have that each point as each node, sorry, as is represented as a point. Each edge is represented as a line. Now just let me add something. So let's create an interactive representation. So, as I said, these SF network objects from this SF network object, we can extract the node dimension and the graph dimension. If we extract this type of dimensions, we can also run the usual function that maybe already noticed. So, for example, we can run a map view code to plot ST as SF SFN nodes, to plot an interactive version of the nodes. I mean, here there are really many nodes. I mean, just show, for example, the first 100 nodes. And then we can add the edges. Oops. Sorry, just give me a moment. Here we can see that we have all these sort of lines, and here if we extract the spatial and the graph dimension, we have like an interactive representation of this type of data. If we zoom out, we can see that this is a region close to Lagos, and it's this type of area. These 100 points are just 100, say, intersection between edges that share at least one point in the boundary. The lines are the segments that represent the roads. For example, we can zoom in a little bit more. We can also change the background, and we can see that actually these lines actually represent the roads in this part of the city. So we have all these type of roads, and for all these type of roads, we have a representation of the line string that belong to this object. So now I just want to briefly, let's say, briefly describe some of the pre-processing steps. These pre-processing steps, they have, I think, the same idea as the operation that I showed you before. And yes, so the idea is that if we start with some type of data, you must be really careful. You must be really careful when you run this type of analysis, since it's really difficult to face some problems. For example, as I said before, here the algorithm that lies behind SF networks creates a boundary point, so create an edge for each shared boundary point. The problem is that usually it's really difficult to determine which boundary points are shared, since the computer has a finite, let's say, finite precision. For example, here I show you just a super toy example. If we check the toy example, here you see that we just added a super tiny error to some of the coordinates. So this 1a minus 8 is like 0.00000001. So it's a super tiny error, but this super tiny error is enough to mess up with the SF networks algorithm. The problem is that when you print this type of data, so you check this type of data, you don't see the problem, since here the coordinates, they're rounded. So here we see that there is a super tiny error. So here it says that here it goes from 20 to 21. The problem is that actually this 20 here is not the same as this 20. Since this is not the same as this, this 20 is not the same as this 20, then the algorithm is, as SF networks, mess up. Sorry. the algorithm doesn't work and creates different different nodes for these two points. For example, when I run this line of code, you can see that the node data has 6 nodes. These 6 nodes are the unique points, so the 0, 0, 0, 1. The problem is that we have a duplicated 2, 0 point. So we have duplicated 2, 0 and 2, 0. These should be the same point, but they are not exactly the same, since this type of data, the first coordinate, has a tiny error, which is enough to mess up with this structure. So if you want to fix this type of problem, there is, let's say, this tool that can be used to round the coordinates. You can round the coordinate using a given number of significant figures. For example, here we use 6 significant figures, and if we run this code, then we can see that actually everything works fine. So the problem is that it's really difficult to diagnose these type of problems, since even if you print the objects here, you don't see any problem. But actually, when you run the code inside, you can see that there is such a tiny error that actually the 2 points are not exactly the same. So here I just want to share, I think, a really funny representation of this type of problems. Here I will show you. So here the idea is that, I mean, usually if you're dealing with this type of data typically obtained from OpenStreetMap, you're working with latitude and longitude data. The problem is that usually let's say the significant figures in the latitude and longitude data are really artificial figures. For example, just imagine that check the 1, 2, 3, 4, 5, 6, the 7th page. The 7th page says that if you are dealing with 1, 2, 3, 4, 5, 6, 7 significant figures, then seven digits, they are enough to pinpoint, let's say, a letter on a book. So, I mean, clearly, if you want to work with the geospatial data, you don't really need that much of precision. So if the input coordinates that someone gave you, they have so much significant digits, then usually, and you want to work with our function, then usually you can round this digit to a significant amount and maybe solve some of the problems that you may encounter. The second tool that I will show you is the one that can be used to subdivide the edges. Subdivide the edges means that we want to create a node for each, let's say, for each point which is shared between 2 or more edges, but not in the boundary. For example, I will show you now. Here we have this type of structure. Oops. For example, for this type of structure, we have that the first segment, it has 5 points, which are colored in green, in red. The second segment has 3 points, which are colored in blue. So these 2 segments, they have 2 intersections. But the problem is that when we run this type of algorithm, we can see that actually there is no intersection, since here it says that we are dealing with an unrooted forest. The algorithm does not recognize that there is an intersection, since, as I said, sfnetworks creates nodes only at the boundary points. And for the red segment, the boundary point is this one and this one. For the blue segments, the boundary point are this one and this one. So here in this case, we have actually that the 2 segments share a space, but they are not really connected. So if we want to connect this set of segments, we have to run the 2 spatial subdivision morpher, and we have to create these we have to transform these artificial intersections into intersections. So then if we represent, let's say, this output, this is the result. So we have the 2 boundary points here and here, which became nodes. The 2 boundary points here and here, which became nodes. But also this point became a node, since in this case, this point is shared between the two segments, and is actually a point that is useful from a routing perspective. So Here, I want to stress that if you want to work with our package and you want to work with this data from OpenStreetMap, this problem is really common. And so I strongly suggest you to always run this type of algorithm before any other operation. If you run, let's say, if you want to analyze data from OpenStreetMap using our package. I will skip this stuff and I will skip this one for the moment. So we can move to, let's say, hopefully to the more funny stuff. For the more funny stuff, I want to show you, let's say, a super simple analysis that focuses on the data from a JG region. So first, let's start from the RJG region and let's convert the input segments to an SF-network object here. As I said, the first step is always to apply some preprocessing operation. In this case, I don't want to create nothing super difficult. The only preprocessing operation that we apply here is the two-spatial subdivision, which creates nodes every time there is an intersection between 2 points, 2 segments that share 1 point, and the two-spatial simple algorithm. The two-spatial simple is the one that we're used to remove the segments that connect a point with itself. And then we transform the coordinates, since usually it's easier to work with planar coordinates than latitude and longitude coordinates. Okay, so now I mean, let's see a plot. Plot SFN axis equal true. So this is the same as before. I mean, it's really difficult to understand the differences, but this is the same plot as before, but we fix some of, let's say, some of the missing links. And in fact, if you remember, at the beginning, we said that SFN was composed by more or less 500 components. Component means isolated segments. Actually, this means that if we fill all the missing nodes, so there are some, let's say, some blanks in the coordinate, and we fill the missing nodes, then we can, let's say, merge some of these unconnected segments, and we can connect some of these components. So now I want to show you the first operation. The first operation is just called spatial filter operation. The idea is the same as the geographical filters. So we have a set of geospatial objects, another set of geospatial objects, and we want only to filter the observation or the nodes or the edges that satisfy a particular operation. For example, in this case, I want to define a polygon given some coordinates, and here I will show you both the data and the polygon. So the points and the line are the same as the nodes and the edges that I showed you before, and the red polygon denotes a particular region that I might be interested in. For example, let's say that you have the network for a complete city, and you want to analyze data just for a neighborhood. If you want to analyze the data just for a neighborhood, you want to filter the data just for that neighborhood. If you want to filter the data just for a given neighborhood, you can run the sfilter function. The sfilter function requires an SF-network objects, a polygonal object which denotes the region that you want to filter, and a predicate. In this case, the simplest predicate is st-intersects. St-intersects says that we want to filter each vertex in SFN that intersect the given polygon. So let's run it. And if we plot it, we can see that actually we consider only the points and the edges that lie just in that polygon. We can also see a little bit differently. So these red points or these red lines are the lines that were filtered using this sfilter function. Again, I mean, in this case, I'm considering just a super simple, let's say, rectangular filter. The same also when you want to consider any type of filter with any shape. Here I just want to briefly stress something. So in this case, we can see that here we are dealing with here we are subsetting, we are creating a spatial filter for the nodes. Actually, if you run the same operation, but you want to create a spatial filter for the edges, this is slightly more complicated, since the problem is that in this case, tidygraph says that if you want to filter the edges, here you can see that the nodes are not filtered, since in principle tidygraph says that a node exists, an edge exists only as a connection between two nodes. But if you remove the nodes, the edges can still the nodes can still exist. The opposite is not true. So the problem is that if you run a spatial filter and you run a spatial filter for the edges, then this type of spatial filter, it works, but it does not remove the isolated nodes. So for example, here you can see that there are some links here, but there is no but several nodes are isolated. If you want to remove the isolated nodes, you can run this line of code and you can remove the isolated nodes. The problem, the second point here that I want to stress is that this type of function, they depend on the active and inactive geometry. As I said at the beginning, this sfnetworks class starts from the tidygraph class. The tidygraph class implements the idea of active data or active geometry. So the idea is that if you want to run a filter or you want to add any verb that is implemented in dplyr using and you want to filter the edges, then you have to specify that you want to activate the edges before running the filter operation. On the other hand, if you want to filter the nodes, then you want to say that you want to activate the nodes and then you want to filter the nodes. Here we can specify two different ways to activate the nodes and the edges. We can explicitly call the activate function, or we can use this shortcut. This shortcut is the usual pipe, but says that before running the pipe, we also want to activate the nodes. So here, this one. So it's like the usual pipe that maybe you have seen in other courses. But here it says that we do not only want to run the pipe, we also want to run the pipe and filter and run the pipe, and says that the nodes are the active geometry. Finally, I want to show you a super simple example that combines this idea and show you that we can use these ideas to detect overpasses in the network. Overpasses occurs every time that there is an intersection between two objects, but this intersection does not represent a vertex. So again, imagine that there is an overpass and an underpass. In a 2D world, these two streets, they are intersecting, but actually there is no node in the intersection. If there is no node in the intersection, actually this intersection is an overpass. So the idea is that we start from the original object and then we run the pipe operation selecting the edge, and we want to filter only the edges that cross any of the other edges in the data. .e means all the other objects in the data. So we want to run for all the nodes, and we want to filter we want to run over all the edges, and we want to filter the edges that cross at least one of the other edges. And then we want to filter the isolated segments, to remove the isolated segments. So this is the output, and we see that, it has a weird structure, but actually, we are really happy, since when we run this type of data, we actually notice that this code can recognize the overpasses. So if we create an interactive representation for this type of data, here, for example, we can see that this type of data actually recognize the overpasses. And for example, this may be useful if you want to, let's say, to optimize some transport operation, if you want to run some, let's say, some code that gives more importance to the overpasses. And actually, this type of data can be useful if you want to detect overpasses in a given street network. So the starting point is just a set of segments, the GG data. Then we convert this type of segments to an sfnetwork structure. And from the sfnetwork structure, we can run some graph operation to filter only the overpasses. Now, just give me 5 minutes more that I want to show you some routing operations. For the routing operations, the key ingredient is that actually sfnetwork is just a wrapper around the graph. So actually we are just running, let's say, the usual algorithms for shortest path. The idea is that here we are creating a weight which is equal to the length of the edges for the given SF network. So we are not, let's say, just trying to minimize a length on the network. We are trying to minimize a geographical length. So we are trying to create actually the spatial shortest path. So if we run this type of code, we say that we want to create a new column which is named weight. This new column weight is equal to the geographical length of the edges. So here, if we print the data, we can see that actually there is a new column in the edges table, which is named weight. So here we have a summary of the edges data. There is a new column in the edges weight, in the edges table that is named weight. This weight gives, let's say, the geographical length of the edges. So if you want to compute the spatial shortest path, we want to minimize the spatial distance between 2 points. I mean, I will run this code, but I will skip this part. And here I want to finally show you some shortest path. To compute the shortest path between 2 points, you can start from the index that represents those points. For example, if I want to compute the shortest path between the first node and the nodes that are number 10 and 100, then I can run this type of code. This type of code returns a table object. This table object has as many rows as the number of shortest paths. So here we are asking for 2 shortest paths. The first one is from 1 to 10. The second one is from 1 to 100. And for each shortest path, we have a list object that stores the indices of the nodes and the indices of the edges that belong to the shortest path. For example, in this case, I say that I want to extract just the first row of data, so the first shortest path, and I want to extract the indices that belong to the path of the nodes. So this index says that the shortest path that connect the point, the first vertex and the 10th vertex has this index. The funny part is that now we can, let's say, finally visualize the shortest path. So the idea is that we can start again from the raw data. We can plot the shortest path here, and we can plot the starting point, which is this green point, and we can plot the final points. So if we start from the green point and we want to reach the red point, this red, let's say, this set of segments are represented the shortest path. Again, if we start from the red point and we want to reach the blue point, from the green and we want to reach the blue, this set of points represent the shortest path. Actually, the same operation can be performed using spatial points. So the input, the input of ST network paths can also be specified using geospatial points. If you specify an input using geospatial points, then this input, then these points, they are projected into the network and they are assigned to the closest point. So the shortest path can also be extracted automatically. So here, I will skip this part. And for the super last part, I just want to show you the idea of isodistance. The idea of isodistance is that given a point on the network, we want to filter only the other nodes on the network that are closer to our given point than a given distance. For example, imagine I can download the street network of my city. I can select the point of where I live. And for example, I may want to visualize all the points in the network that are closer to my hometown or to my house, that are closer than 1 kilometer. For example, I want to have an idea of how many, let's say, facilities I can reach in 20 minutes walking. We can perform this type of operation. I will skip the details on the code. I just want to show you the result here. Oops. So the idea is that we start from the same network as before. So the green points and the green lines, they represent the same network as before. The idea is that if we start from the black point, we can use this type of code to select all the nodes that are closer than 1 kilometers to the black point. So the idea is that, for example, if I know that it might, for me, it takes, I don't know, 15 minutes to walk for 1 kilometers, all the supermarkets, bar, restaurants that are within the area, I can reach all these places in less than 15 or 20 minutes. So this is the idea of the ISO distances. The idea of the time is the so-called isochrone, and actually we can, let's say, we can translate this idea from ISO distance to isochrone in a more formal way, but it's not important now. And I think that's all for the presentation. I just want to conclude saying that if you have any problem running our code, if you have any issue, whatever, we have a discussion page on GitHub. Discussion page on GitHub, it's here. And here it shows that if you have a GitHub account, you can just create a new discussion and ask any questions. If you run our code and you face any bug, then you can also raise a bug. So you can also say, no, I actually ran this code and I found this bug. Please help me solve this type of bug. If you have any question and you, for example, you want to run some type of analysis and you don't know how to do that, then please create a question or create a discussion or create a question on Stack Overflow and add the tag sfnetwork. So that's all, and thank you very much for the attention.